Alright, chapter 13, test review. So this is ionic equations, or net ionic equations, and colligative properties. So we're going to start with net ionic equations. The one we're going to work through for that is the one in your book on page 440. So on the PowerPoint slide, we've done it before. Will a precipitate form if solutions of potassium sulfate and barium nitrate are combined? If so, write the net ionic equation for the reaction. So we're going to write the chemical equation, the overall ionic equation, the net ionic equation, and identify any precipitates that might form. So potassium sulfate, well, sulfate is SO4 with a -2 charge. Potassium is K with a +1 charge. So that's K2SO4. It has to be aqueous. Plus barium nitrate. Barium is a +2 charge. Nitrate is a -1 charge. So I have to have two nitrates. That's going to yield, maybe I can fit it, KNO3 plus BaSO4. Now we don't know what these are yet, aqueous or solid, so just going to put these down here. And we've got two potassiums and two nitrates, so I need a 2 here to balance. So we're going to go to that table on page 437, figure out what my products are. Alright, potassium, sodium, potassium, ammonium compounds are soluble in water. Rule number 1. They always are. So I'm going to have to look at the rest of it. That's aqueous. Let's do this a little better. Okay, so barium sulfate, that's the next one I have to look up. And let's see, we've got number 6, most sulfides. Sulfides, remember that's just S. Number 4, most sulfates are soluble except barium, strontium, lead, calcium, and mercury. So this is barium sulfate, so it's an exception. It is not soluble, it is insoluble, therefore it gets an S because it's a solid. Alright, well there's my overall equation. So let's just write my net ionic equation. Or sorry, my ionic equation. So K2, 2K, that's a plus charge, that's aqueous, because the whole thing is. Plus SO4, that's a 2 minus charge, that's also aqueous. Plus barium, 2 plus charge, that's aqueous. Plus 2NO3, it's a minus charge, that's aqueous. Plus 2K plus aqueous, plus 2 NO3s with a minus charge, that's aqueous, running out of room, plus Ba with a 2 plus charge. Wait, do I write Ba and SO4? Well, it doesn't ionize because it's not soluble. Okay, so since it's not soluble, I don't do that part because it's not soluble. It won't ionize. It won't dissociate. Right? It doesn't do anything. So I have to leave it as is. So BaSO4 solid. So that's not an ion. Now we go through and we figure out what we call our spectator ions. That is, what's on both sides of the equation that haven't done anything. Well, Ba and SO4 did something. They combined. I got a 2K plus over here. I got 2 potassium ions on that side, and I got 2 potassium ions on that side. So they obviously haven't combined with anything. All right. I also got 2 nitrate ions there. And I got 2 nitrate ions there that still have not combined anything because the potassium nitrate, as long as it's in solution, won't actually combine. So the only thing that I actually did was combine barium and my sulfate. So that is my precipitate. If you have to identify your precipitate, barium sulfate is my precipitate. That is my solid that comes out of solution. And my net ionic equation is just the part that makes it. Now the first 2 parts are going to be aqueous because they had to be to split, so they could then rearrange and combine, and they form an insoluble, non-ionized product. So, chemical equation, overall ionic equation, net ionic equation. Okay? So that's how to do those. Alright, colligative properties. So let's do a freezing point elevation. we will do just one of the sample ones in the book. So let's go through sample problem, or practice problem 1A. Now let's just do the sample problem so I don't have to do too much math. So we'll do sample problem C, page 449. What is the freezing point depression of water of a solution of 17.1 grams of sucrose into 200 grams of water? What is the actual freezing point? Remember, if I'm asking for the, if you see the word change or freezing point depression, or change and boiling point elevation, what that means is I want just the delta T part. If it says what is the freezing point or what is the new temperature, that means find the change and combine it with your original starting point. So here it says what is the freezing point depression? So, and then what is the actual freezing point? So part A is just the change, part B is what's the new temperature. So 17.1 grams of sucrose, so C12H22O11, that has a molar mass of 342.34 grams. 342.34 grams per mole. So first off, I get this into moles so I can get molality. Grams of sucrose. 1 mole. Sucrose. 342.34 grams. And I get 0.0500 moles of sucrose. Now I divide that by my molarity, which are my grams. So 200 grams molality equals moles of solute over kilograms of solvent. So 0.0500 divided by 0.200 kilograms, and I get 0.05 divided by 0.2, 0.250 mole solution. Okay. So that's my concentration. Now, my freezing point depression, well, I have my original equation. Word stopped working. There we go. We're back in business. So my T of F, so my change, because the triangle means change in my freezing temperature equals the constant for my solvent solution times the molality. Now I know this is water. Water is negative 1.86 degrees Celsius for every mole concentration I have. And then my molality, which we just calculated, was 0.250 mole solution. So I do that math. And I get negative 0.465 degrees Celsius. Now that is my temperature change. All right, this is water, so I start with my original freezing point, 0 degrees, plus negative 0.465 degrees Celsius to get my new answer. So my new freezing point equals negative 0.465 degrees Celsius in this case also. Now, that's only works for water. If we were doing another substance, it would be different. Excuse me. All right, so that was a non-electrolyte. So let's go ahead and do an electrolyte solution. So what is the expected change in the freezing point of water of a solution of 62.5 grams of barium nitrate, all dissolved in 1 kilogram of water? So 62.5, no, 62.5 grams BaNO3, 2. All right, so we divide it by the molar mass. The molar mass of barium nitrate is 261.35 grams. So divided by 2, 61.35. And that gives me a grand total of 0.239 moles of barium nitrate. Okay. I know the molality because this is in 1 kilogram of water, so conveniently this is also a 0.239 mole solution of barium nitrate. And then I just have to figure out my freezing point. So my equation, T of F equals K of F times molality. This was in water, so I have negative 1.86 degrees Celsius for every mole concentration I have, and a 0.239 mole concentration. So I do that math, negative 1.86 times 0.239, and I get a negative 0.44454 degrees Celsius temperature change. But that is only for 1 mole of the substance. Now, barium nitrate, being an soluble ionic compound, when it hits water, it dissociates. So if I put in 1 mole of barium nitrate, I actually get 1 mole of barium and 2 moles of nitrate out of it. So I actually get 3 moles out of this whole thing. And a colligative property depends on the concentration and how much I have, not what the substance is. So I have to multiply this by the 3 moles of ions I get. That's not going to be an actual unit, this is just where it's coming from. So I'm going to multiply this by 3, and I'm going to get a negative 1.33362 degrees Celsius temperature change, negative 1.33 degrees Celsius. That is my new temperature change. Now, new temperature would be negative 1.33 degrees Celsius as well, because we were using water. Now let's say we weren't using water, okay? So I have my negative 0.4, well, oops, sorry, I'm getting ahead of myself. Let's say we're going to do this in ether. Okay? Now, ether has a normal freezing point of negative 116 point, lost my chart. Chart page 448, negative 116.3 degrees Celsius, my normal freezing point, and my normal freezing constant is negative 1.79 degrees Celsius for my molar concentration. So I have to change my numbers. Now the equation is still the same, and I already know the molality. The molality, if I was going to do the same thing and just put it into ether, is still the same. So my molality is still over here, my 0.239 molar solution. So I can still say 0.239 because the number of moles I had, we're going to change it, but my constants change because it's no longer water. So instead of negative 1.86, I have negative 1.79. Okay, so negative 1.79 times 0.239 gives me negative 0.42064 degrees Celsius as my temperature change. All right, times the 3 ions that this actually turns into. And I get a temperature change for ether if I dissolved my 62.1 grams of, or 63.1 grams of barium nitrate into ether of negative 1.26 degrees Celsius. Now that's my temperature change, right? The delta T of F. That's not my new freezing point. My freezing point is my starting point, which is negative 116.3 in this case, plus the 1.26. Negative 1.26, so I have negative 1.26 plus a negative 116.3 for a grand total of negative 117.56 degrees Celsius. Okay? Because my starting point in this case isn't 0 anymore. So that is how to do a net ionic equation and colligative property calculations. Now remember, the other equation that we have is change in boiling. That's my boiling constant times molality. Just different numbers. Remember, this number, if it was water, is 0.51. It's positive. There, I don't think it's negative. Right? If it's a boiling point, it needs to go higher. If I add something to a solution, it increases the boiling temperature. Remember, on the test, you need to know water. You need to know K of F and K of B for water. I'm not going to give you, so I'll give you the chart for solubility. I'll give you the freezing point chart on page 448, but I'll give you everything except water. So you need to know those two values for water as well as the starting, freezing, and boiling points. And then we could rearrange these. I could solve for the constant by dividing my temperature change by the molality. I could solve for molality by dividing the temperature change by the correct constant. So those are just variations on the same equation.